So first of all, thanks for the invitation. It's lovely to be here today. You've perfectly introduced the title of the paper is Frictionless Inflation. This is joint work with Miguel, who's joining us today and hopefully helping me with some of your questions. And Xuan Wang, who's an excellent second year PhD student who's currently at the University of Minnesota. And we really hope we have high expectations of his work. So, keep track on him. I'm currently visiting Minneapolis Fed. So as I guess most of you are well aware, the classical disclaimer does apply that, nothing here is going to reflect the views of the Fed. Let it be the Minneapolis or the board. Okay, so let me jump directly into the motivation of this paper. Menu costs are one of the most widely accepted explanations for why we see prices adjust really slowly. In models that features this kind of menu cost, what really matters for inflation dynamics is not just the observed price, but actually the price between the actual price, and the firm's desired or optimal price, which we call frictionless prices. The challenge with this type of models is that these desired prices tend to be unobserved in the data. And the literature has often overcome this challenge in one of two different ways. More traditionally, researchers have often relied on numerical methods to try to reduce the state space, because this is an infinitely dimensional object we're not observing. So the goal is to reduce the state space to be able to solve the model structurally and therefore give predictions entirely from the theoretical perspective. And perhaps more recently, there's a strand of papers that has been trying to figure out what are the sufficient statistics that are able to summarize the key predictions of this model. Either of these two approaches that are kind of very common nowadays share the fact that they sidestep the core unobserved state that drives inflation in this model. And this is exactly where the focus of our research or this paper is going to be at. This object, which we're going to call frictionless inflation, and we're going to define as the inflation rate that we would observe if prices could adjust, if firms could adjust prices in the absence of menu costs. Okay. Let me just go directly into the question. What we're interested in is, first of all, understanding whether this object, this frictionless inflation notion that we're going to be pushing, can tell us something interesting about inflation dynamics. And providing that I'm able to convince you at the very beginning of the talk that, in fact, it's an object that's worth looking at, how can we actually recover it from the data? Like, how can we do an empirical estimation of this object? So we see the paper as structured around three main components, and this is going to also follow the outline of the talk. First of all, we're going to go back to a very simple and standard model of price setting, a random menu cost model, and we're going to bring frictionless inflation to the center of the analysis. We're going to do this by just revisiting the optimal pricing rule that results from this model, what we call the SS rule. And then we're going to be able to decompose the inflation measure in the model into two different components: a frictionless component that's going to capture somewhat of the fundamentals or the shocks to actual prices, and then the part that kind of captures price misalignments or the stickiness or frictions in the model. And hopefully I'm going to introduce some of the uses that we're thinking about giving to the object, but the one that I want to stress today, the insight that I want to push forward, is the fact that frictionless prices in these models tend to precede changes in actual prices. So with that, we think that frictionless inflation is going to look like a leading indicator for actual inflation, and that's what we're going to try to pursue by looking at it.
Good. Okay. So the first thing was just bringing frictionless inflation to the center of the analysis. The second step is we're going to be developing a methodology to recover frictionless inflation from the data. So for that, we're going to first start by rewriting the model in state space form. And by state space form, for those of you that haven't heard this term before, we simply mean we want a framework where we have some unobservables, which we're going to call the states or latent states or hidden states, and some observed variables, which we're going to have as the measurements. And then all we're going to be looking at is two sets of equations. First of all, the law of motions for those hidden states, and then some mapping between the states into the measurements. That's really what I mean by rewriting the model in state space form. This is going to be useful because then we're going to be building on state space methods to estimate both the parameters that govern the relationships of these equations, but also the hidden states themselves. And I think the contribution here, or our strategy, is that we're going to be very careful on how we exploit the structure of the optimal pricing rule. So this SS rules that we've been talking about in the first part of the paper, to first of all solve for the filtering problem of the states, and second, providing some proposal distributions for the variation estimation that we're going to do later on. So once that this will be much clearer when I go through it throughout the entire presentation. This is where we're going to spend most of our time. So if it sounds a little bit kind of mysterious at this point, it's okay. I'll kind of get to it a little bit later. Then I'm going to show you how we take the algorithm to the data and look at one particular application. So we're going to be looking at UK CPI microdata. So this is going to be the universe of locally collected price quotes that the official national statistic uses to make up or put together the CPI. So this means that we're going to be using millions of quote lines ranging from 1996 up until 2018. We're going to be estimating, as I was saying, the parameters of the model and recovering the frictionless inflation at the item level. Finally, I'm going to kind of circle back to this first insight where I said, you know, in the model changes in frictionless inflation and frictionless prices precede changes in actual prices. I'm going to show you that once that we estimate aggregate frictionless inflation, we can use it to improve the forecasting accuracy of actual inflation. So in that sense, we believe that this is an empirical object that's very interesting if you are thinking about where the economy is moving next. So in terms of where we fit relative to the literature, I think the paper contributes in 4 different strands. The first one, you know, there's a bunch of different papers that have been looking at price setting under menu costs. I could list an infinitely long list of papers, just a couple of them, Golosev and Lucas, Nakamura and Steinson, probably the most canonical now at this point. I'm also kind of looking at Auclair et al. Because that's going to be the version of the simple menu cost that we're going to be using. What's the contribution here is, as I was mentioning in the motivation, we're going to kind of make this key latent state the object of interest. And this is something that has been mostly ignored in this literature. And like the whole point of a lot of these papers has been how to solve for it, how to solve for the model without having to estimate it empirically. And we're going to take this different approach where we're going to try to go and estimate it empirically. A little bit more related in a narrow set of papers within the price setting under menu costs, there's a couple of other papers that have tried to estimate alternative empirical measures of inflation. Perhaps the most known is the reset price inflation measure by Bills, Clino, and Malin in 2012. What we're going to be doing differently is that they are using new price data, and they're implicitly assuming that the behavior of adjusters is informative to some degree of what non-adjusters would like to do. So it has this very strong assumption on the relationship with these two type of price setters. We're going to have a very different approach. We're going to still rely on the model, but we're going to contribute in terms of the methodology because we're going to move into this state space estimation that I'm going to explain in a second. More towards the econometrics, there is a literature on estimation of nonlinear state space models. Here, kind of the contribution is going to be claiming or showing that SS models are a particular good setup to do grid-based filtering and smoothing at a very big scale. So we're going to do Bayesian estimation and the filtering at the quote level. This has some intricacies in itself, and we're going to kind of claim or show that the SS model is particularly good for this kind of exercise. And then finally, given the application that I'm going to be discussing today, which is, remember, inflation forecasting, we're obviously going to be related to papers that have been thinking about what is the best way to forecast inflation, let it be econometrically or with some model-based. We are kind of proposing a new model-based predictor, which is this measure of frictionless inflation that I'll discuss by defining the model. So we're going to have a very simple random menu cost model that you might have come across if you've been working with this type of models or even your first year, second year PhD classes. We're going to think about a firm I that's setting prices in logs in a discrete time framework. PIT is going to be the notation that we're using. We're going to be comparing that to its desired price, noted by PIT star, which we're going to assume follows some random walk with drift. So the drift here, you can interpret it as the positive trend inflation. And it's going to be receiving some idiosyncratic shocks that are going to be kind of determined by a volatility sigma square epsilon. The firm is going to be incurring some quadratic loss, which is going to be increasing in the gap between the price it's setting and the price it would like to set. The reason that the firm is not going to be able to close this gap at each point in time is because they have to pay a fixed cost every time they want to adjust their actual prices. And we're going to be relatively flexible in how we think about this fixed cost. We're going to assume that with some probability lambda, this fixed cost is equal to 0. So that's like the arrival of what we're going to call a free adjustment opportunity. And this is basically allowing for some Calvo-ness in the menu cost model, right? This is kind of a time-dependent friction that we're going to be able to accommodate in the model. With the complementary probability with 1 minus lambda, however, the firm has to pay a fixed adjustment cost, which is going to be constant. It's going to be the same for everyone, and it's going to be positive. So this is kind of the menu cost component of our model. This is the state dependency part that we're going to be including over here. So given this kind of key set of assumptions, it's often very useful to redefine or write the problem of the firm, not in terms of prices, but in terms of the price gap. That's the difference between the price your firm is going to be setting and the price that it would like to set if the world was completely frictionless. With that, the kind of of the firm's problem is just to choose this price gap such that it minimizes the path of the price gap, by the way, to minimize expected discounted losses. So we're going to be accounting for the loss associated to the price gap, just as we defined it a second ago. And also any time that you're changing the price, you're going to have to pay for whatever the realization of the fixed cost is. If it's Calvo, it's going to be 0. If not, it's going to be this constant measure C over bar. With that, you can go through any of the papers, and here we're relying on the Auclair et al. Paper, but all of these papers kind of show that the optimal pricing policy that results from this type of problem is what we call an SS rule, right? So what we observe is that firms are going to keep their prices constant for a while, and they're going to be adjusting infrequently. When is it that they adjust? They adjust under two possible scenarios. The first one is if they receive a free adjustment opportunity. That means that they receive the adjustment cost equal to 0, which happens with probability lambda. It is also possible they adjust even though they don't have a free adjustment opportunity whenever the price moves outside what we know as an inaction region, right? And the inaction region is going to be determined by a lower threshold X bar T and an upper threshold X over bar T. So when the firm decides to adjust, it's going to set its gap equal to some optimal level, which is going to be captured here by XT star. If it doesn't adjust with the rest of the probability, what's going to happen is it's going to allow the price to drift and therefore the gap to drift passively according to the trend inflation component and also any realization of the idiosyncratic shock to the frictionless price. So this is kind of the summary of, this is really what we need for the model that we're going to be working. We want to have an optimal pricing rule where there's some probability of adjustment and you set a new optimal pricing gap. And there's some complementary probability of not adjusting where you're just going to leave the price drift. In general, of course, the parameters of this rule, so by parameters here, I mean the reset point and the bounds of the inaction region are going to be time varying. That's why you have a subscript T. However, in the steady state, these three objects are going to be constant, and we're going to be working with approximations around the steady state. So for us, we can look at these three objects as being constant parameters, which we're going to be able to estimate. Having solved the model, then the next thing we want to do is just basically rewrite the definition of inflation that we have in the model and separate or decompose it into two components, right? We have inflation dynamics now that are going to be governed by two different objects. The first one is our measure of frictionless inflation, and let me just define it once again in the context of the model. It's just a change in the frictionless price. That's the price that the firm would desire, would like to set in the event that they didn't have to face the menu costs associated to adjustment. And then the other part is going to be the change in the price gap. That's like this second component over here. So with that, you can already see that this identity is going to help us understand some sort of historical decomposition of what has been driving inflation over time. We can think of the frictionless inflation as being the part that's driven by the shocks or the fundamentals. And then the other part is just going to be the kind of the catching up from the previous shocks associated to the fact that we have frictions. So this is one of the applications we're currently looking at. We think it's particularly interesting in understanding the asymmetries when we think about the surge and the retreat of post-COVID-19 inflation. For this, this is kind of what we're currently working on, not that we're going to be focusing on today. The second application, which is probably the most interesting for some of the people here, especially for policymakers, is that if you're able to decompose actual inflation into these two sides, you're able to say how distortionary current inflation currently is. And this might give you a notion as to how aggressive you might want to be when fighting inflation, because there's a part of it that might be non-distortionary and therefore monetary policy might not have a say. Finally, the one thing that we're going to be focusing on today is more of a forward-looking approach, and it's this idea that to the point that frictionless inflation is more, it's more persistent, it is more smooth. I see a hand up. Can you take the question?
Yes,
Yeah, just a small question to avoid confusion. So in standard models, like the new Keynesian model, wouldn't the frictionless inflation be zero? I mean,
exactly. I mean, so like it's not that it would be zero. There's still going to be some frictionless inflation. It's just that how distortionary that frictionless inflation would be constant over time and would be picked up just by the friction. With menu cost models, that might be changing, and that's why we think that on the current measure, you could have this decomposition on how bad is it currently.
like if demand changes, there's a demand shock, and prices should adjust. When there are no menu costs, I would assume that prices adjust immediately. So there's like a one-shot, one-time adjustment, and everything is done. So I'm confused.
In the Calvo model, you're gonna have firms adjusting over time. So eventually, it's true that they catch up, but to the point that you have to wait until your Calvo shock to be able to adjust. You're gonna be having some gap between where you are and where you want to be. And then there's also going to be if you're expecting the shock to have some persistence, you might be overreacting today relative to what you would do if you were able to adjust at every point in time. So there's those two things. There's going to be this time side that's, there's still going to be some friction there because you're not able to adjust at every point in time. And that's also going to force you that when you are able to adjust, you might overreact anticipating that you won't be able to adjust in the future.
Just the last question to make sure I understand, like in the Calvo world, frictionless inflation is here in the menu cost model world. You mean by frictionless, no cost for adjusting prices, right?
Yeah.
in the Calvo model, it would be that the ferry arrives each period, or?
Exactly. That's
Okay.
right. That's exactly a point.
Okay, thank you.
Thank you very much. I just have one question too.
Go for it.
Is it so maybe related to the first point about ex post and what is driving inflation? So is it possible that frictionless inflation, which is a very nice decomposition, would also capture things that are not friction, things
So
like
you're
behaviorals,
yes,
non-rational behaviors, stuff like
it's
that?
going to capture like not only non-frictions, it's going to capture any friction that's outside the menu cost. Like let me just like when we say frictionless inflation, it's frictionless in the context of a menu cost model where the type of friction that we're featuring is this very specific. To the point that you might, I mean, there's a bunch of other frictions that you can rewrite as a menu cost, and then we would be fine. It's just still labeling, but there might be other frictions or other, like deviations from the standard model, rational expectations, or some sort that I'm not capturing. That's going to be kind of picked up by my frictionless inflation measure. I would need a kind of, a more complicated model to be able to estimate it. And depending on how complicated it is, I guess we could accommodate it. We're just starting with a benchmark menu cost model, the simplest version that's more, but yeah, basically it's anything else that's not the menu cost friction that I have in this type of model.
Okay. Thank you.
So, but it is true that in the model, and we'll see that this applies in the data, this object is going to be more persistent. It's going to be smoother, and therefore it's gonna be able to anticipate what's happening with actual inflation. And let me give you just like a very clear example of how this is by using simulations from the model, right? This is just graphically. If I were to plot, I'll have to take a firm. I'm going to be plotting its frictionless price over time. This is my blue line over here, and we have the trend inflation. That's why it's going upwards, and everything's in logs. This is what's underlying the decision process of the firm, but this is not what we observe. What we observe is something closer to this, right? This is actual prices. We see that they're constant for a long time. Then something happens in the model. That's because you have a free adjustment opportunity, or because the gap has been widening enough that it now compensates for paying the menu cost. And in that case, there's something happening. It's an increase in the price. There's this jump at T1, then we're going to be stuck with that price for some time, and then eventually we're going to have a second of this event. So this is what we're observing in the data. If we put the two of them together, it's kind of, and you're willing to eyeball, it's easy to see that we need some activity or some movements in the blue line to happen before the change in price actually realizes. So to this point, it's easy, like it's intuitive to kind of argue that the blue line is going to be a leading indicator to what's happening in the black line. And to that extent, we're going to be exploiting this as a use of frictionless inflation. Good. Okay, so that's for the model. Very simple. Hopefully something that you've seen before. We're accommodating Calvo-ness, so time dependent, but also the state dependent frictions. And having you convince you that this is something that's worth looking at, the core of the paper is how do we go and estimate it? Given that we have this, how do we go from here to this blue line using the data? And before I get to how do we do it, I'm going to redefine, I'm going to change a little bit of the notation of the way we're looking at prices, because that's going to be easier to kind of show the analytical results that we have. So the first thing is we're going to be looking at not frictionless prices directly, but something I'm going to call the reset price. And the reset price is going to be defined as the price that's going to make the price gap equal to the reset point. Remember that when I was defining the SS rule, I'm defining the SS rule in terms of the price gap. And in the event it changes, in the event there's adjustment of prices, the price gap is equal to some X star point. So then this reset price is simply my frictionless price plus the reset point. Because this is constant, we're looking at stationary equilibrium. When we look at inflation rates, the two things are just going to be equivalent to each other, but it's going to help in how we write and how we identify some of the parameters. So having introduced this new reset price, there's two things that change. The price gap is now, we're going to look at SIT instead of XIT. And that's going to be the difference between the price and the reset price. Again, the reset price we don't observe. It's just a hidden state in the same way that the frictionless price was. The other thing that changes is that when we rewrite the SS rule, our inaction region is now going to be given by two different thresholds, S lower bar and S upper bar, where we have to adjust accordingly to the reset point. So we're just moving everything, we're moving it down actually, relative to the X star. So from now onward, when I talk about the price gap, I mean the price gap relative to the reset price. And when I look at the inaction region bands, I'm looking at them once they're recentered. So just keep that in mind. It's a little bit of a caveat, but it doesn't really change much of the intuition that I'm going to be explaining. An additional notation, we're going to be using LIT as a dummy variable that's going to be indicating whether the firm receives a free adjustment opportunity or not. And then we're just going to collect some of the terms. First of all, I'm going to look at a vector of latent states. What are the latent states here? The first and obvious is going to be the reset price. That's what I'm going to try to kind of uncover. That's the whole point of the paper. But also the free adjustment opportunity is going to be important. That's something I don't observe. I don't know whether the firm changes its price because it's free to do so or because it's happy to pay the positive adjustment cost. And that's really what is going to help me uncover this reset price. So I'm going to collect them and call XIT the vector of latent states. The other thing I'm interested in estimating is going to be model parameters. I'm going to collect them under the vector theta. What are the model parameters here? It's going to be two parameters that govern the evolution of the frictionless price, so the trend inflation statistic, and also the volatility of the idiosyncratic shocks to frictionless prices. Then we're going to have the evolution of the free adjustment opportunity. This, remember, the lambda is the probability that you obtain a free adjustment opportunity. And then finally, the two key variables of the SS rule are going to be captured by the inaction thresholds. Here you can see why rewriting things in terms of the reset price helps. This is because we're going to kind of summarize the SS rule by these two parameters instead of having a third parameter, which would be the reset point. So that's going to make our lives a little bit easier, and we're not going to be able to separately estimate the reset point from these two. This is the reason why we needed to go through the hassle of a little bit of a new notation. Good. Okay. So then it follows pretty naturally that there is a state space representation of this model. And let me argue why. First of all, we have some unobservables. Those are our latent states. And we have some observables or measurements, which is the actual price. That's the data that we have. All we need is some equations that explain how these latent states evolved, and another equation that explains how the observable depends on the latent states. So this is going to be given by the model. The first one is the measurement equation. That's just describing the evolution of the measurement or the evolution of the observed variable, which is just the firm level price dynamics. This is exactly the SS rule that I was describing a second ago, just written in a different way, right? So what we have here is that our observable is a function of the past observable and our hidden state. Just to kind of go over it again, what we have is that prices are going to be either the price yesterday, assuming that you don't adjust. So the D here is an indicator of inaction. And in the event that you do adjust, what you're going to set is your price equal to the reset point. So we're writing the optimal pricing rule in terms of prices instead of the price gap. That's all the difference. What is my inaction indicator? Same as before, but the other way around because we're looking at inaction instead of action. So when am I not going to adjust? I'm not going to adjust provided I get I need to pay for it, so no free adjustment opportunity. So if I need to pay for my adjustment opportunity and my gap is within the inaction region, then I won't adjust. And assuming that I do get a free adjustment opportunity, there's still a chance that I choose not to adjust. And that's the case when my price is actually to where I would like to be, right? This is going to be mass of 0 when we take it to the data, but this is just for completeness. There is a special case where you might receive this free adjustment opportunity and you might want to give it up because you're exactly at the point where you want to be, and therefore it doesn't make any sense. That's the measurement equation. The transition equations is just the evolution of the latent states. And again, this is given by the model. For the reset price, it's going to inherit the exact dynamics of the frictionless price that I gave you at the very beginning. So it's going to be a random walk with drift, same parameter for the trend inflation, same parameter for the volatility of the shocks. And there's going to be also some functional form for the evolution of a free adjustment opportunity, which we are writing in terms of the new LIT variable. So these two equations, together with the observables and the unobservables, are going to give us the core of a nonlinear state space system. All we need, the one thing that is missing, is some assumption on the initial distribution of states. We need to know, or we need to impose, where is the initial gap going to start with? And this is something that we're just going to take as given. We're going to run it, and then eventually the initial conditions are not going to matter. So it doesn't really matter where we started. One thing that's important, up until now, I was mostly talking about a single firm. It was denoted by I. But when you look at the data, what you have is a balanced panel of firm level prices, right? And that's what we're interested in. We're interested in the panel. So what we're going to do is we're going to expand the state space representation for a number n of firms. So no longer one, but we're going to have I going from 1 up to some capital N. So we're going to impose two assumptions to be able to do that. The first thing is we're going to assume that the parameters are constant for all the different firms. So everyone has the similar law of motion for the frictionless prices. The volatility of the idiosyncratic shocks are going to be the same. You know, like we're going to assume that the parameters, just like in standard models of menu cost or in standard models of price setting more generally. The other one we're going to be imposing is that the idiosyncratic shocks, as well as our assumption for initial distribution of states, those are going to be IID across the different firms. So these are the two conditions that we need to be able to augment our state space representation from a single firm up to a panel of firms that we're going to take to the data. With that, the next step or the goal, what we want to do is we want to develop state space methods, which is simply going to say we want to estimate our vector of states for every single firm at every single point in time, together with the parameters that are going to govern the relationships between the latent states and the measurements, as well as the evolution of the states themselves. So the parameter vector theta. We're going to do it in two different steps, or at least my explanation is going to come in two different steps. The first thing is we're going to be characterizing the forward filtering problem that's going to be allowing us to recover what are the states given the information that we observe, provided that we take a vector of parameters constant, right? So we're assume that we know theta, then we're going to be solving the forward filtering problem. However, we want to do these two things simultaneously. So we're going to be introducing, we're going to do it in, we're going to go Bayesian here, and we're going to introduce this forward filtering step as part of a Gibbs sampling algorithm where we're jointly estimating the latent states with the parameters. So it'll be clear in a second, but we're going to do it in two steps for expositional purposes, but these two things are going to be done simultaneously, and we're just going to be alternating one and the other. Okay, so forward filtering. So what is, you know, for those of you that it's been a while since you saw a forward filtering problem, what is it that we're trying to do here? So forward filtering simply means that you want to update your belief about the firm's hidden state. Remember, the hidden state is the reset price and the latent state. the free adjustment opportunity as we observe prices over time. So for every period, what we're going to do is we're going to use the model's transition rules to project forward from the past state. And then we're going to use the new observation, the new observed price, to update that projection. And this process is going to go recursively, and it's going to go period by period. That's really what we're trying to do. So we're going to use, we have a past state. We're going to project what we think it should be based on the rules from the model. And then we're going to use the new information to update that projection. And we're going to do this recursively. Formally, the problem looks as follows. This is just the standard definition of forward filtering problem. All I want you to take away from here, if you've seen many of this before, is that the joint densities, so this is the filtered density, and this is the one step ahead density, both of them can be written as the product, or can be factorized into the product of individual densities, right? So this is for all the different firms, and I can kind of simplify it into the product of the individual firm density problem. That means that our recursiveness, right, the fact that we're going to be, 7 is we're projecting, and then 8 is we're updating, and we're kind of feeding one. We're starting at some point and recursively mixing 7 and 8. We're going to do this at the firm level. So we're going to recover a trajectory of individually filtered distributions, and then we're just going to multiply them to get the joint density. So you can see how the parallelization is going to help us when we get to scalability issues. Of course, forward filtering is normally considered a one-sided estimate because the data you're using is up until the point where you're going to be updating your belief. That's why you're looking at data from 1 up until period lowercase t. If you want to use the entire set of data that you've got available, so you're going to be using data beyond the point where you're updating, you're going to have to incorporate a backward sampling step, which you might want to do or not, depending on the application that you're using. And I'm happy to talk about this later. It's going to be a very similar problem, and it's going to have this property whereby it's also going to factorize in the same way. I'm going to spare you the details, but if you're interested, it's in the paper, and the intuition that we've just kind of that I'm going to be explaining in how to deal with this is going to apply. But just to let you know that there's a backward sampling problem, and we're going to be talking about it when we think about the algorithm. But it's just once you understand the forward filtering, it's really what you need to do. So this is the definition of the problem. How do we go and solve for this problem? Normally, you would use the Kalman filter and look for closed form solutions. What's the issue here? The model is it's highly nonlinear. Why? Because the as-is rule, remember, gives you this step function. It has kinks. It's very nonlinear, and it's also very non-Gaussian because of the free adjustment opportunity. So we're not going to have closed form solutions to be able to solve for these recursions. And instead, we're going to try to use numerical methods to approximate the integrals over here. And then the key thing is, how do we discretize the state space, right? How do we narrow the state space so it's something that we can handle on a computer? The main idea here, and what we think makes SS models very kind of interesting framework to exploit state space methods and look at this filtering, is that we're going to be using the kinks to our advantage, right? One key thing in this type of setup is that the measurement equation, which is the SS rule, is going to be completely deterministic. That means that given the observation, we know exactly which hidden states are compatible or not what we observe. Let me explain a little bit of how this works. So suppose we look at the data and there's no price change. What do we know? What do we learn from that? The first thing that we learn is that the firm did not receive a free adjustment opportunity, right? Because otherwise it would have changed its price. So that's the first thing we do. We kind of eliminate the possibility that LIT is equal to 1. But then what happens to the reset price? We don't know exactly where it is because there's no price change, so it's not equal to the price that we observe. But we do know, conditional on the parameters, that it has to be within the inaction region. So we are kind of narrowing we're narrowing where it can be landing in terms of the grid that we want to kind of construct. What if we do observe a price change? Then we have far more information. The first thing that we observe is the reset price, because when prices adjust, they are set up to be equal to the reset price. That's the way I've defined my reset price. So we're going to kind of reduce the uncertainty on the on part of the hidden state massively. We now know where we are. And if the price is very small, and very small is going to be determined by relative to the inaction region, if it's small, it must have been that the firm received a free adjustment opportunity. So here we're done. We have both states. If we have a small price change, we know what is the reset price, and we know that there's a free adjustment opportunity. If the price change is large, we still know what the reset price is. What's a little bit more uncertain is what is the adjustment opportunity. We don't know if it's equal to 1 or it's equal to 0. However, in any case, we just have two different options. That's reduce the state space massively. So we're going to be using this property of the model, the fact that it's going to be bounding, the SS rule is going to be bounding the latent states to construct time-varying grids and weights for latent states. This is going to allow us to concentrate all the computational power where it's exactly needed. And this is going to speed up massively the filtering step, allowing it to be very accurate. Okay, so this is filtering. Filtering, as we were describing and the way we've defined it, is conditional on knowing what are the parameters, right? We're assuming this for a given set of parameters. However, we need to estimate those parameters, and we're going to do it. We're going to go for a Bayesian approach, or we're going to do both things together. So we're going to assume the parameters and states are going to be random variable, and we're going to use the data to basically estimate what is the distribution of each of them. And we're going to do it in a Gibbs sampler. So a Gibbs sampler is just basically another iterative algorithm where we're going to be basically assuming we're going to divide parameters, and we're going to assume two blocks, parameters on the one side and hidden states on the other, and we're going to be alternating on which one we keep constant. So first, or like you choose how you want to start, but we sample on parameters conditional on the latent states, and then we do the other way around. We sample on latent states conditional on the different parameters. So the second part is what we've already kind of covered. We are going to be looking at how do we do the two of them simultaneously. So one thing that is key in the Gibbs sampler is choosing the right distribution from which you're going to start sampling. And for that, again, we're going to use the framework that's provided by the model. So there's a subset of parameters, which is most of them, for which we're going to use conjugate priors. That's going to allow us to have a very like a closed form solution for this step. It's going to be quick. It's going to be straightforward. There's nothing really interesting. If you've done any Bayesian estimation, this is going to be entirely straightforward. There is a subset of parameters, however, for which we're not that lucky. And we're not going to be able to find conjugate priors, and therefore we're going to have this additional step that's often known as, well, it's actually known as Metropolis Haston. Which are those parameters? The bounds, the inaction region threshold, the lower bar S and the upper bar S. And again, we're going to use the model to our advantage to kind of speed up and make this step a little bit easier. I'll explain it in 1 second. Then finally, as I was saying, for the second block, we're going to be embedding this forward filter and backward sampling whenever relevant for the latent state. This is what I was just explaining a second ago. Before we go into these two steps over here, let me emphasize that we're doing Bayesian estimation at the micro level, right? We're doing this for the quote at the quote level. So scalability is going to be very, very important to us. And the way we're going to be able to achieve it is thanks to two different features of the model. The first one is the conditional independence across the quote lines. Remember when we're describing how do we go from a state space representation of a firm to a state space representation of a panel? We said we're going to assume that the shocks and the initial states are going to be independent. That's going to allow us to parallelize the estimation and then speed up the calculations. And the other thing is intrinsic to SS models, and it's the fact, as I described in a second ago, that the latent space it's very low dimensional. The fact that once that the measurement equation is deterministic, we know exactly where the state conditional on parameters, where the latent states might be. Okay, so on the variation estimation. The first, for the subset of parameters for which we have conjugate priors, those are going to be the trend inflation parameter, it's going to be the volatility of the idiosyncratic shocks, and it's going to be the probability of a free adjustment. Those are going to be guided by economic theory. They're going to follow a normal, an inverse gamma, and a beta. And as I was saying, standard with conjugate priors, the conditional posteriors are going to be derived analytically, so that's going to speed up and make it very simple, this part of the Gibbs sampler. What happens to the bands? What happens to the band? Like, how do we get the Metropolis Hastings? So Metropolis Hastings, again, for those of you that haven't done Bayesian for a while, what you have to do here is you're going to be drawing a candidate value from a proposed distribution. You're going to compare it to the data, and you're going to see whether it matches the data better or worse than the previous candidate. If it does a better job, you keep it. If it does a worse job, well, depending on how much worse, you might keep it or you might discard it. What we want to do is we want to exploit the fact that in our model, and this is probably a third or fourth time that I repeat this, the measurement equation has no noise. It's deterministic. That means that once you conditional on the states and on the parameters, the likelihood it's either 0 or it's 1. So a proposed value is consistent with the data or it's not consistent with the data. This is going to help us in how we build the proposals, distributions, because we're going to write them, we're going to kind of select them in such a way that the values are always going to produce a likelihood of 1. We're just going to choose the supports of the distribution that generate values that are going to be consistent with what we observe, because we know whether it's possible or not.
Nora?
Yeah.
I just have one question about that. So do you assume that the model is I mean, maybe I'm wrong, but when I'm reading and hearing this, I assume that the model is a perfect description of the reality. But there could be model inconsistencies or model issues that would not catch all the reality, and then saying that there is no noise is a bit hard.
So we're doing we're in a sense, we're doing a semi-structural approach in that we are assuming that the price setting is coming. It's a perfect description of how the firm is setting prices. So to that point, we're kind of taking that as given.
Okay.
Right, Miguel? I want to say like.
So the no noise. I think there's two important things. So one thing is we're tying ourselves to a random menu cost model. So the measurement equation comes from that. The no noise, it's not our assumption. The no noise, it's an assumption of the random menu cost model. Because if you know the states, you know where your gap is, and you know whether you can adjust for free or not, the rules implied by that model, it's either you adjust or not, and there's no noise in there. So the noise is not our assumption. We're tying ourselves to a random menu cost, but the no noise, it's a property of that model.
No, I guess that the problem is like, I think the question would be like, if the model is misspecified, we're not going to be able to pick it up.
Yeah.
No, or in another way, you can put this like my first question. So what you are catching is also model misspecification, which is related to behaviors and all these things that we raised at the beginning.
Absolutely.
So saying no noise would force the model to catch other things than frictions.
I agree. So we're interpreting it from the lenses. In that sense, it is a semi-structural approach. That's the structural part. Is we're kind of interpreting this data from the lenses of the model. So to the point that the model might be a bad characterization of what's going on in the data, we might be mislabeling stuff that we're picking up with a frictionless inflation.
Okay.
So like the no noise, maybe that's something we should. I should
Yes.
have a different bullet point over there. Is once we buy into the menu cost model, the measurement equation is deterministic. That's really what I mean. But it is. I understand where the confusion of no noise comes from. But it is. This is again. It would be like from the lens of the model, the measurement equation is deterministic.
Yes.
That's kind of
yes.
the correct
So
way.
from the lens of the model, meaning that there are model misspecifications that could
Exactly.
change the
Absolutely.
Okay.
Yeah, that's
Okay,
right.
thank you.
And that's why it's not entirely, it's still it's semi-structural. Like we don't go, and I guess our view is, all these different approaches, both the numerical method one that goes fully structural, but also the sufficient statistics ones are very much grounded on the entire structure. We're able to kind of I think reduce some of the assumptions. We're kind of taking away some layers on rigidity, but we still need some of it. The very big part that we need is the SS rule, and that makes it semi-structural. So we're kind of bringing less layers of structure, but there's still some there. And to the point that that's there, everything's going to be through the lens of the little structure that we're imposing. So it's a fair point.
Okay.
And the way it's written here is a little bit confusing. Yeah, question?
Yeah, we have a question from Amit Friedman.
Hi, thanks. As much as I understand state space, if the measurement equation has no noise, it just means that this is a definition.
I agree. Yeah.
Okay.
Yeah, that's fair. It's like, yeah, basically we can, what we're doing is we're using it to uncover, based on the definition, what is feasible and what it's not. And with that, we're doing two things. We're kind of simplifying the filtering problem, and then it's also helping us in determining what is the proposed distribution for the metropolis Hastings. Does that make sense?
Yeah, it's just, I think it's, for example, if you take output, right, you can write a measurement equation and define output to be the sum of potential output and the output gap. Both are latent. The noise is zero. It's just a decomposition of output by definition. That's all.
I agree. But in the measurement equation, that's right. The measurement equation, however, has the two hidden states, and the consistency varies on the realization of those hidden states. So it's not that straightforward as a decomposition. We need to do a little bit more of a step on what we see. That's why the size of the change matters. It's like if we didn't have the adjustment, the free adjustment, it would be a little bit easier. But because we have these two things moving at the same time and affecting the actual price, we need to do a little bit more work on decomposing it.
Thanks.
Okay, so again, we're going to choose proposed value. So we're going to build this proposal distribution so that anything that you, any value that you get is going to yield this likelihood equal to 1. So mathematically, this is what it's going to imply is that the ratio, the likelihood ratio is going to cancel in the acceptance rule. So which are these two facts that we're going to be using? And we're just twisting things in different ways, but we're essentially twisting the same thing. So the first one is the fact that all price gaps, the observed, remember here we're conditioning on the latent states, and we're conditioning on all the other parameters except for the inaction region. So once that we have price gaps, and we have them because we're observing the price and we're conditioning on the hidden state, all of those must lie within the inaction region. So this means that the inaction region has to be wide enough that it accommodates all these price gaps. That's going to impose that the lower bound has to be large enough, cannot be too large, and at the same time the upper bound cannot be too small. So that's going to impose an upper bound on the lower threshold and an a lower bound on the upper threshold. That's what's gonna help us construct some of the proposal support. The other fact that we're going to be using is that when we see a price change that is related to a non-free adjustment, and again, we're conditioning on the hidden state, so we know whether it's 1 or 0, those price changes have to come off outside the inaction region. So again, that's going to help us redefine and narrow what the proposal bounds should be, and therefore generate supports that are going to give rise to values with a likelihood equal to 1. And that's kind of the core of the algorithm. That's, we're going to go back to over here where we're going to be doing this alternating sampling with the parameters conditional related on states, parameters, some of them with conjugate priors, other ones with the metropolis hastings. And then we're going to switch things around and we're going to be sample the states, conditional parameters using the filtering step that I described a second ago. And with that, we're done on the methodology, and we can move to our first attempt on the application. And here's where we're very much open to feedback on what other things you think might be of interest. So we're going to be looking at UK micro price data provided by the ONS. That's, as I've mentioned earlier, the universe of local collected prices, quote levels, in over 140 locations. We're looking at more than 500 items, and the data is going to be from 1996. The data for today is going to be 1996 to 2018. The stuff we're working with just at the moment is expanding to include COVID. So that's one caveat to keep in mind. We're going to be looking at regular price path. That means that we're going to be cleaning very much in line with other papers that use microprice data. So we're going to be dropping sales. We're not going to account for substitutions. We're going to think of that as a new price. And one thing that's particular to our cleaning procedure is that we need to work with quote lines that don't have missing observations, because it's very important for the filtering that you have continuity. So whenever there is a missing observation, we're just going to break the quote line and think of them as two independent quote lines, so we can keep on doing the algorithm as presented. Also pretty standard with cleaning procedures in this literature. We're just going to look at items where we have enough price changes so that we can infer something. If a price doesn't change over time, there's very little we can say. There's nothing we need this price changes to be able to do all this inference when it comes to what is the underlying reason for that price change. There's also a little bit some details that I'm going to spare you on how do we move from quotes to indices, because we're going to have to do this in different levels. We're going to first, and this is consistent with how the ONS uses the microprice data to generate the CPI inflation measure. We're first going to use geometric means to construct aggregates at the stratum level, and then we're going to be using chain link month to month to do to aggregate things to the item. Once that we have the item level, remember that's where we're going to be estimating our model, especially we're going to be estimating the parameters to be equal across a given item. Then we can aggregate using official weights to have an aggregate CPI or an aggregate inflation level, which is in the end what we're interested in. Let me run you through the estimation of the model parameters, right? So we're doing this for every single item, and we're going to be reporting, the average of each of these parameters, and then some measurements on how to capture the heterogeneity. Two things that I'd like you to take away from here is that if you look at the mean, at the average, it looks very much like prior findings in the literature. It doesn't really matter whether you're using US data or UK data or some other papers looking at European data. What we find is that on average, trend inflation in a monthly setup, it's like something like 0.1%. The idiosyncratic shocks, the volatility of idiosyncratic shocks is 9%. And then the Calvo-ness, which I think goes back to there's this, a lot of the literature that has been thinking about menu cost model. The whole debate is whether the model is more Calvo or more state dependent. We find that at a given point in time, the chances of having a Calvo shock or a free adjustment opportunity is something like 14%. So the model is Calvo to some extent, but not enough that we don't care about the distortionary effects of frictionless inflation, which for us, when we're thinking about the policy implications, is really important. The other thing to take away from here is that once you move beyond the average, there's a lot of heterogeneity across items. This is something that we believe is very interesting, and we're trying to exploit in terms of validation of the model. We're still working on it. Any ideas on whether you think particular sectors would be more interesting are obviously welcome. So this is done at the item level. We estimate the parameters, then we can recover at the quote level frictionless inflation. We can aggregate it up first to the item level, then to the aggregate level. And here we have our final measure of frictionless inflation. So we're reporting two things. We're reporting in black what regular price inflation is. This might not map directly into the core headline inflation measure that the ONS provides, because we're just using our sample. That means that some items are not there. That means that we're going through some cleaning procedure that the ONS does not. But in general, it looks very much in line, especially the swings are kind of related to what your headline core inflation measures would look like. But this is kind of the benchmark that we want to compare our estimates to. And the estimate of frictionless inflation is here in blue. What do we find out? We find out that the gap between the two ranges between negative 0.79% and 2.29%. So sometimes it's up, sometimes it's down. The average is 56%. And this measures both of them are highly correlated, but not perfectly correlated. So the correlation is something like 0.83. We compare the volatility of the two measures, and as we were describing, it turns out that frictionless inflation is smoother than actual inflation, so that this relative measure is 1.24%. In general, we see, and this is already kind of anticipating where we're going, is that especially as we move over time, it's kind of very clear that movements in frictionless inflations tend to precede changes in the black line. So this is where kind of we can already anticipate that it looks like frictionless inflation is going to be a good leading indicator to actual inflation. So let's test for this more formally. Instead of asking you to believe what I'm saying, we're going to be borrowing a simple forecasting exercise from Blinder and Rice back in 2005. This paper, what they're trying to argue is that core inflation is a leading indicator for actual inflation. So we're going to kind of borrow their setup to argue that frictionless inflation is a good leading indicator of actual inflation. So what they're doing is just basically regressing inflation rate between periods T and T plus H, where H is going to be the forecasting horizon. And they're going to regress that on either monthly year, 12 months before year-on-year inflation, or the equivalent measure of our frictionless inflation, or just include the two of them. So we're going to have like three different model specifications. One where we just have past inflation, another one where we have past frictionless inflation, and the third one where we have the three of them. And the whole point of this exercise is to see whether this frictionless inflation measure that we've estimated has additional information beyond what's already kind of a part of past inflation that might be useful for forecasting. And these are our results. We're going to have 4 different forecasting horizons: 6 months, 12 months, 24 months, and 36 months. And we're going to do 3 sets of exercises. The first one is an in-sample regression, where we're going to be using all the information that's available, so from 2000 up until 2018. And we're going to be reporting the 3 different models we were discussing: just frictionless inflation, headline inflation, and both of them at the same time. Our measure of success here is going to be the in-sample standard error. So the lower the standard error, the better we're doing. And what we find is that frictionless inflation does better than headline inflation. And this difference is going to be amplified as we increase the forecasting horizon, right? So the gap between the two is going to be increasing over forecasting horizon. What happens if we include both of them? We do better. Like, it is true that we do better, although the biggest difference comes from switching headline to frictionless more than adding headline to the frictionless. So the gain in terms of reduced standard error is not as big as it is when we just move from one to the other. But just to keep that in mind, both of them are going to be obviously better. A different exercise is if we do an out-of-sample forecasting performance measure, where we're going to be using data up. We're going to be running the model up until 2008, and then we're going to be forecasting from there. We obviously find higher standard errors because we're using less information, and we're doing, like, the exercise in itself is tougher. But the main message holds, whereby frictionless does better than headline. And that difference is going to be, again, increasing the forecasting horizon. Here, including the two of them together, increases performance forecasting quite more than it did before. But again, the biggest difference is coming from the frictionless component more than the headline component. The last exercise is more of a horse race. We're just going to be reporting, the coefficients, what are the numbers, and in particular, what is the significance level, whether they're statistically significant or not. And what we find here is that frictionless is always significant, whereas headline is not. And the significance level is going to be increasing as we expand the forecasting horizon. So altogether, frictionless does better than headline. And how much better it's going to be increasing with the forecasting horizon. That's kind of like the biggest takeaway from this exercise. And with that, let me just, I have no idea how I'm doing in time, but let me just conclude. The whole point of the paper is thinking about this measure of frictionless inflation. I'm just going to conclude, and I'll take the question in a second. Let me just be very specific. This comes a lot in the questions, and it's a perfectly valid point. We're thinking about the inflation rate absent menu cost, so anything that can be written in terms of a fixed adjustment cost. We use that kind of definition to decompose inflation into fundamentals and frictions. I think this historical decomposition might be interesting. We're in the weeds of getting results there. For now, we show it's a leading indicator of observed inflation. So we thought it was a good idea to kind of try to estimate it from the data. We do it with a state space framework where we're going to be leveraging this as rules for doing some efficient filtering and Bayesian inference. We did a first attempt to apply to UK CPI microdata, where we find a lot of heterogeneity in the pricing behavior across the items, and more importantly, the frictionless inflation measure that we are able to recover is smoother and more persistent, and this improves the forecast accuracy over past inflation measures. Thank you. And then I'm happy to take the questions.
Thank you very much, Laura. So please raise your hand if you have any questions. We will start with Charles Lichfield. Charles?
Thanks very much. I'm sorry for interrupting. I just wanted to get in the queue early for the questions at the end. It's a simple question just on how you define a free opportunity to adjust menu costs. I didn't get why sometimes this was free and sometimes this wasn't. But otherwise, thank you very much for a very interesting presentation.
Okay, so this is what Nakamura and Steinson call a Calvo plus model, and it's an attempt to, that's the definition, like their definition of a random menu cost. It's just this idea that we want to incorporate time-dependent and state-dependent nominal rigidities at the same time. So the way to do it is, normally you would have in a menu cost some constant cost associated to change prices, but with some probability that is going to collapse equal to zero. So that's the way of accommodating both of them. We're just, again, following here, there's nothing really new we're doing. We're just allowing for the more flexible version of a menu cost model, and it's the original Nakamura and Steinson. They call it the Calvo Plus, and the version we're doing is the Auclair et al. the QG, I think it is.
Thanks.
Thank you. Yossi Achim?
Okay, thank you. Enjoyed the presentation, very interesting paper. I have a question or a comment about in what sense is the measurement, should we treat the estimate as a frictionless inflation? So of course, it's clear from the theoretical model you presented why you call it frictionless. But I would like to see maybe a little bit more of validation exercises from the data. And let me suggest two of them. One, you mentioned that, okay, frictionless inflation turns out to be smoother than actual inflation.
Mm-hmm.
I just wonder, just in the most simple, the simplest new Keynesian model, for example, I guess it should be the other way around. I'm not sure. Because if you can adjust your prices every period, maybe you'll get something a little bit more volatile, but simple simulation, I guess. The answer for that is I guess, to get the answer is easy, just to check the model. So that's one thing I would check. The other thing is connected with policy. I guess frictionless inflation in standard model, not only New Keynesian. If there's no frictions, monetary policy is neutral.
Mm-hmm.
The central bank moved the interest rate. Real rates remain unchanged because there's no because of neutrality. So this means inflation goes one-to-one with interest rate. So I would suggest an exercise where you give a monetary policy shock and try to see, let's say on headline inflation, hopefully inflation goes down, but frictionless inflation should go up. So the fact that policy is able to contract the economy and reduce inflation comes from the friction. And in that sense, I would say, okay, what you measure is frictionless inflation. So these are my comments. Thank you.
Thanks. That's great. So let me just to make sure that the second point, I think it's a great suggestion. We'll take that on our to-do list. That's a fantastic point because we're struggling on how to make this point on the policy relevance, and this is kind of building on together on the sex, and it would be a great validation exercise. The validation exercises that we've been working on so far have to do more on exploiting the sectoral differences and looking at whether we do find that the difference between frictionless and actual inflation are bigger in those sectors for which we know that prices are more rigid. In terms of like there is some common, I mean, again, it's going to be there's some consensus in the literature that these are sectors not looking necessarily at the prices, but there is a belief that there should be more frictions for how price setting works. So that's where we're going, but this is also a very good point. Let me clarify on the first one. So on the first one, you're just thinking about, can we validate using model simulations that the frictionless inflation should be smoother? That's the point that you were saying, right?
Yeah.
Like this is because we're discussing this, I guess yesterday, Miguel and I, whether it's obvious or not, whether this should be the case or not. So that's a good point. We can use a model to simulate and see whether it goes in line. Thanks for the comments. Those are really
Thank you.
Thank you very much. So we have an additional question from Evangelos Stravelas.
Yeah, hi. Actually, this is really nice work and impressive work, I would say. I'm just curious about your intuition during the 21-23 inflation episode we had with the supply disruptions and much higher inflation. My question is, would you expect your menu cost to have mattered more or less during that period? And could you frictionless inflation measure provide useful insight for that episode? Thank you.
So that's a great point. I have a short and a long answer. I mean, I have like a more satisfactory. So like what we're trying to do with the 21-23, with the surge and then with the retreat, is whether to see there's asymmetries, whether, you know, on it, what does it take? Like it might be the rising prices. It's more like the shock that drives what we observe versus lowering prices. We have the other way around. That's what we're trying to do. Whether the role of menu costs has changed over time, we can do a hand wavy exercise like over here. The way we interpret the fact, look like when we look at the data that we, sorry, this I'm gonna have to go until the end. We were interpreting in a previous version of the paper the fact that the gap between frictionless and actual inflation is bigger in the past and then kind of slowly kind of collapses. We were interpreting that as the role of rigidity is falling over time. So this could, you know, we could do a similar thing with the COVID episode. I'm saying it's a little bit hand wavy because in the model we're not accommodating for changes in the role of menu cost. So we would have to do a time varying. We would need to allow one of the parameters to be time varying to be very like to do this properly. And yeah, we could potentially do it. We haven't done so. I think that if we find something interesting on this asymmetry that we're discussing, we might go that route to kind of go a little bit deeper on exactly what's going on there.
Thank you very much. Laura?
Yeah.
Okay, so I have several questions, but I will not ask them. I will send you some comments by email. So I just have one maybe stupid question. So why you did not include or tried to work with Markov switching models? Because those are maybe more adapted to catch states.
I'm gonna defer that to Miguel because he's the.
Yeah.
Well, you could. It's a good point. I guess it's a little bit of path dependent. So we go here. So in say ours and Leapy and all those models, typically the assumption is that B stars follow Brownian motion with drift. So we just made that the continuous time, the random walks, kind of the discrete time analog to that, to kind of to talk with those. We could have a Markov switching, say for the shocks of the P star, make it discrete. Actually, because they are grids, we could nest adjusting a couple of things, but the methods would be able to handle that.
We've kind of discussed this, Miguel, correct me if I'm wrong, when we're thinking about changes in trend inflation.
Yeah, so
because for now trend inflation is constant, but you know, like we can either do windows where it's constant, or we could kind and take a stand on when the window ends and starts and finishes. Or I think in our ideal world we would have a regime switching where it's the trend inflation that switches regime every now and then and estimate that as part of the algorithm. That's I think where we thought it would be an interesting framework.
That's my next question.
Yeah.
But yeah, so just my 2 cents on that. I think my if I can help. So maybe you know the RISE toolbox that allows you to compute Markov switching and nonlinear models and estimate Bayesian estimations of Markov switching models of GSG models of this kind. So maybe it could be useful. I just have the second question, so it's very related to what you said, Laura. Is when I see this figure, so first of all, very technical point. So maybe you can compute distance correlation because the behaviors are nonlinear, even if what I see at least, and also maybe try to as a first test, but I think it's very related to what you said, maybe run some small sample estimations or at least correlation. So what's happened before the crisis, what's happened after, The correlation is the same after, is the same before, different, why? And also in the same vein, maybe having a specific analysis according to where is the level of the interest rate, where is the state of the economy or GDP, if we are below 2%, above 2%, if we are at the zero lower bound. I think it could be very, very interesting, and I think it could explain some gaps you have here.
Okay.
At least I see one or two here. So, and I think this could be very interesting from a policy perspective if it is what you asked before. Yeah. So I will try to send you by email some of my remaining comments. I have others, but in any
Please
case,
also include the references that you're saying about the just write
yes.
like we're both taking notes, but it would be great to see your
Sure.
own notes on even this comments.
No problem. No problem. Yeah. And my last point and my last question. So, okay, so we discussed, you presented a very interesting model, a fantastic data set and application, very technical. I think it's a very complete paper, and I really enjoyed this presentation. But now, as a policymaker, how I could use your product? So that's also why I asked the previous question. But now I'm a policymaker, how I could use your product.
So I think it goes back to the question on like the validation. So out of the way I see, we started with the easiest thing, I think, that in terms of this forward-looking kind of thing. But the one that and if this is me, Miguel might completely disagree, the part that I'm really excited about, especially on the policy implications, is thinking about this current application. And here the idea is, according to these models, not the entire part of inflation is distortionary, it should be only the frictionless. That's what like monetary policy, that's the part that you should observe responding to a monetary policy shock. So to some extent, if you are to write an optimal policy problem in these models, which is it's not trivial and it's hard to see, it's only most of the times it's very structural. Kind of the idea is that you might not have to respond to all inflation surges in the same way. It should be, you should be able to do this decomposition of, is it distortionary or not? And this would give you a measure of how distortionary current inflation is. And I think that's kind of the biggest takeaway, that in the same way that you look at the output gap or you look at inflation expectations, you could use this as a measure of, if I'm responding with, like, let's say a Taylor rule, it might not be a Taylor rule that is entirely responding to actual inflation, but to frictionless inflation, or more specifically to a change in the gaps. I think that's where I see it's still not, we still haven't polished the argument. And we're working on how to kind of use the model to show this point in the simplest way without having to go fully into the optimal policy problem. But that's where I think we're going, in that, the whole discussion about whether hyperinflation is good or bad is how much of this is distortionary or not. This would give you a real-time measure of how distortionary inflation is. I think that's where I see it. Miguel, if you have any additional.
Oh, that's it. I mean, in policy would be points 2 and 3, right?
Yeah.
I guess policy doesn't care too much about what's in the past. So yeah, point 3, I think we are getting there. It's all that Laura said, point 2.
Okay, so let's say, okay, your reply is very interesting, and but then it would raise two questions. So the first question I ask about the model misspecifications, the things that are above frictions that are included in the distortions, and also the fact that there could be, at least in this presentation, maybe there is in the paper, but there is no proof that this is the optimal measure of inflation that would lead to the best performance of monetary policy.
No, that
so, okay.
That's what I'm working on. That's one of the things that we're trying to. So the argument is there in other papers, like it's like that's where on how deep we want to go into the theoretical proofs, is that it's not new, like it's not something new, but it's not nicely put in any of the papers. It's like one of these intuitions that people that have been working with these models think it's obvious. But I don't have a reference, like I cannot borrow from someone else directly and kind of put it into my paper. So that's where we're having the debate on, is it worth it to go entirely in? And, you know, given that the contribution is not going to be the point, it's just the formalization, or whether we're fine with just giving the intuition, borrowing from other people's. So we're having that's, you know, I would love to hear your thoughts. So like, do you think it's worth putting the work on showing, because to some extent it's always going to be model dependent, and you know there's going to be
not in this paper. I don't think in this paper I think you have a very complete paper already, and I don't see the marginal gain on this paper. But maybe you could take what you have done at the beginning from the theoretical model, and then and then add an extension, a theoretical extension that would treat the optimal monetary policy question, and after maybe use the same database to test if it is working, or maybe more macro variables, but at least to check, at least theoretically, how optimal this measure is compared to others. So a theoretical part and an application with more data to see if it is working or not.
So what we had in mind was thinking, you know, it's still reduced form, as you know how in the new Keynesian model we do optimal policy, and then we do implementability, where we have like Taylor rules, and then we say, suppose we, like, you know, you got Lee book chapter 5 where you have open economy, it's hard to determine what the optimal policy is, but then we compare what if we have, you know, Taylor rules with a CPI inflation targeting versus PPI, and which one does better. That's kind of the argument there, which is, it's a kind of shortcut. So we were thinking of doing something similar with a Taylor rule with actual inflation and see how that performs in a menu cost, and a Taylor rule with frictionless inflation and see how that performs in a menu cost. That would be a shortcut, and then do that in the data and see how, you know, policy in the UK would have been different, and whether we had started, maybe we started tightening before we actually did, because frictionless inflation starts going up earlier than actual inflation, and see how that would have played a role. Like, it's not fully there, but it's giving you an insight on, you might want to incorporate this when you're doing policy making decisions.
But this is the third paper for me, in my opinion, because for instance, I have two papers that shows that Taylor rules are not matching best historical behaviors of the interest rate. There are a lot of papers in the literature that are showing that Taylor rules, and there are various Taylor rules. There is no one Taylor rule. There are a lot of rules that are matching better. So I think it would be more an empirical exercise. What I'm talking about is more optimal, you know, commitment, discretion. If you want to apply, then use optimal simple rules, but still optimal, not necessarily Taylor. Yes, I would see this as another paper, but still very interesting. And I would really suggest you to use something else. I mean, as a robustness check, something else than Taylor rules. You could be surprised.
No, I know. I agree. We also have, I mean, we have a couple of follow-up papers with this methodology. Some of them are more on the investment side, and those, you know, we're working with Isaac Bailey and Andres Blanco on that side. And then we have on the pricing side a follow-up paper with evaluating hyperinflations and looking at the cost of inflation. We're using Brazilian data, microprice data there. And I guess the goal there is to think about also strategic complementarities and how that changes a little bit our perception of how inflation might be distortionary or not. So yeah, we'll keep this in mind on the optimal side, moving on that direction for follow-up papers.
You mean we will have to reinvite you in next year?
That would be amazing.
Yeah, I think so. Okay, so if we don't have any additional questions from the attendees, okay, so Laura, thank you very much for this fantastic presentation. very great paper, rich model, and more rich data set and empirical investigation. Again, excellent presentation and a very exciting paper. So Laura, thank you very much. And we wish you a lot of success with this paper and your other projects.
Thank you very much. It's been wonderful, and thanks for inviting me.
With pleasure. Bye-bye. Thank you very much.